So very brief introduction again to me. I'm Ruben Bridgewater. I'm a software architect and Node.js consultant and also Node.js collaborator. Today we're going to talk about fast code and how to actually save some money by overcoming bottlenecks. One of the big questions, of course, does performance matter at all, right? And how many of you have run into issues before? Can you just raise your hands? It's actually quite a few, especially in JavaScript. People tend to get into trouble there because when you're using Node, for example, you just have a single thread, right? And on the browser side, it's not much different, even though the browser does handle it a little bit different. So we definitely have multiple issues there, and often people forget how things work underneath their framework that they're using. We became very lazy in just relying upon code, that is given to us. So we are using AngularJS, we are using React, and so on the front-end side. We are using a whole bunch of Node modules, and we just take for granted how they function. We often do not look into the code base, check if it is actually the right algorithmic complexity or something like that for something that it is doing. And later on, we have some trouble because the website is not loading properly or the application is not responsive enough. So 40% of all users actually abandon the website if it takes longer than 3 seconds to load. And this is not a very new study. It's already a few years old, so I expected the number to be lower by now. 50% of all users expect the page to load at least in 2 seconds. When you're now on this little network, like with the phone, it becomes even more critical. And no one normally likes to really wait on something that long, right? I would not want to use any application that takes too long. And I would try to find something different instead. The main problem in this case is not only the users where we lose a lot of money because you lose your customers by that. But a lot of applications nowadays are hosted on cloud platforms. You're using cloud providers. It doesn't matter if it's like Amazon, Google, Oracle, or etc., right? There are so many out there. What you pay is you're paying for the CPU time, you're paying for the memory usage, you're paying for data transfer. It always depends on what explicitly you're doing. Normally you have like a little amount upfront that you're allowed to use for free, and then afterwards it becomes more and more expensive. So you should definitely pay attention to that. And there is one other side to cloud providers. When you're having a memory leak, things can become very expensive. So performance is critical, and you should always make sure everything works properly. What is performance optimization, though? It is removing unnecessary work. And I love that, Just isn't he cute, right? I mean, you want to cuddle him, he's lazy, I love to be lazy. I study math, you say people who study math are lazy. And that's pretty much it, we want to be lazy as well. So let's remove the unnecessary work. And how can we identify parts that are not necessary in our code? We write a lot of code that is not necessary. It's typical. We just do it that way. Me too. I'm not perfect. So one of the first things you have to do, or the first thing you have to do, is to find the actual bottleneck. If you do not know what the main performance is costing in your application, then you will optimize a lot of parts and waste hours and hours on parts that may just run once that are not actually the downside in your application. So it's really critical that this point is done properly. You have to know what to look for. So we have to profile things. And as soon as we have that point, well, we want to find out why it is actually so. And then we want to make it fast. Normally you set a specific goal. Let's say you want to have a specific API response in a specific amount of time. For example, 50 milliseconds, just random number. That's your goal. So first of all, you were at 200. Now you optimize your main bottleneck. You reduce the total time to 100 milliseconds. Now you just do it again. Profile again. check what is your current bottleneck, because it might have changed since you removed some former unnecessary work, and now there is another point coming up stronger than before, and you want to remove that until you reach your goal. Don't optimize after that goal, because it becomes more and more expensive when it comes to the time you have to invest to make your application faster after reaching a specific point. So what tools are there to identify our bottleneck? There are some built-in things like --prof and --prof process, which you can use in Node Core. That's like the very basic thing. It's something built in by V8. Also, similar, the Chrome DevTools. It's pretty much the same internal functionality. It doesn't look awesome, but it's pretty straightforward. And you can create a flame graph for synchronous code. But flame graphs won't show you things where you're waiting for remote procedure calls, for example. But if there is like a function really hot, and what does really hot mean? It means this function is executed over and over. It's like a lot of time of your application is spent in this specific part of the application. Then it will show up in the flame graph as really hot, red, probably, and a big part of it. And you have some other toolings that I would recommend to use. That is Node Clinic, and it will provide you, for example, with information about if the event loop is blocked, if you're having a memory leak, if you're having some basic problems. It has flame graphs built in, and it also has, as the only tool that I know, a way to analyze asynchronous performance problems. It's called BubbleProf from Node Clinic, and it's pretty cool. Give it a try. But to actually benchmark these things, you also have to produce load on your server. You have to produce really something to do, otherwise there is no function executed in the first place, right? To do that, you can use autocannon, which will then, if you're having a web server, fire a lot of requests at your server that you created up front as a mocking part or whatever, so you can create artificial load. And that's pretty nice. And you can, of course, write all micro-benchmarks, but please always be aware that when writing a micro-benchmark, V8 might optimize some code away. So you have to be very careful how to write them. That code is actually somewhat used. Otherwise, it might just trigger that code elimination, and you think, wow, this code is really fast. Yeah, the part in the loop, it's just gone. We don't want that. Types of bottlenecks. So what bottlenecks exist, actually? One very common one is the event loop is blocked, because there's a lot of synchronous code going on. And how to overcome that is you want to distribute work onto other cores. So you want to have multi-threading. That might be workers, if you have like a really hard, complex algorithm to work on. You, of course, want to remove the unnecessary work, which is often about the algorithmic complexity. And streams is there in case you are having, for example, I/O or any data flow, pretty much. And then you can distribute it into smaller chunks, into small parts. And with these small parts, everything is going to go much smoother, and you can continue running other code while the code is incoming, while the data is incoming. Memory usage is too high. It mainly means you have a wrong data structure. And again, try to use streams, because streams normally reduce the amount of memory that you have at that specific point of time. Then there is more about synchronous code that you can delay. For example, I've seen when you go out there as a consultant, you see a lot of weird things. And people are delaying validations. But validations are always synchronous. You have to check if something particular is in an object. Then you check, okay, is this part in my object? Delaying it doesn't make a lot of sense in this case, and you just create a lot of promises or other wrappers around it that create more work for the CPU. Instead of just doing the work right when it is needed. We often have the trouble that you do not see what part is actually slow. That's finding the bottleneck. And it's often not maybe even your code. Mostly it is, probably, but sometimes it might be something very different, something that you would not anticipate in the first place as being slow. For example, console log was, until at least Node.js 8, really slow. And it turned up in flame graphs as a main bottleneck for applications from big customers. So we optimize that internally in Node, but don't always take something for granted. Sometimes run a benchmark on your own, and if you think this is too slow, complain about it in the module. Or maybe even better, open a pull request to optimize something if you see that you can do something better. And there are a lot of modules that you're using that won't have the best algorithm implemented. A lot of people love functional programming as well. I do like it as well because it has the points that it is normally very concise code. You can read it well. It has the immutability. Awesome. If you want to have fast code, it's really bad. So if you're having like a hot code pass, this is not the right thing to do. Because each time, for example, you're using map, filter, reduce, whatsoever, you always create a whole array again. And then you throw it away. Like if you're doing multiple operations after each other, you're copying everything once. You have to allocate a whole array. And that's a lot of work that you have to spend there. So don't do it if it's a hot code pass. Otherwise, yes. But let's get down to the big O notation, which hopefully everyone knows who has studied computer science or something like that, which means you're approximating the time and memory usage that is needed for the algorithm to complete, depending on the input size. And let's go into more detail about that. So here, we have the O1, O log n, O n, and so on. So this is the different complexity levels from an algorithm perspective. And when you have just 1,000 elements that you have to iterate over, O1 is always constant time. It is always just one operation that the CPU has to do. So this is really, really good. And the logarithmic thing is also really, really good. We want to have those two. Linear is already a little bit more complex, and depending on how big your data is that you have to handle, it might be more expensive than you might anticipate originally. Everything that is above n log n is really bad normally. You cannot prevent it in all cases, but almost in all cases. Like if you're having an O(n) to the square algorithm, it's very, very likely that you're able to optimize a lot out there. Everything above that, we don't want to talk about it at all. Here, there's another view about it, how much work you have to do, just a little bit differently visualized. And what are actually these in JavaScript? So constant time means, for example, an access in an array, which is super fast, or when you access properties on an object, or in a map. They, like objects and maps, they are slower than an array, but it's still constant time. They are using a hash internally to access the right property, but they have to first calculate the hash. And this is always the constant time that they have to use on top of the array access, because the array is just pretty much, I want to have this element, and internally there is a pointer to the memory directly. And then I just get that out of the memory at that point. This is super fast. Better is not possible. Log n, binary search, I just wrote down here. We have to be really brief, so I'm just going to skip through. Linear, well, we have a regular for loop, right? But also, we have the index off. There are a lot of hidden costs when you're using array functions. And not everyone anticipates those as being linear, especially when you think about shift, for example. Shift just removes the very first element of an array, and this is pretty much O1, right? You just take out the first element. But internally, what happens underneath is that when you remove the very first element, the whole array has to be moved. All other elements afterwards have to be moved one to the front. And that's super expensive. And when you're having something like that in a loop, it becomes more expensive. When it comes to shift, there is a small optimization by V8 that is triggered for small array sizes. That is why you probably do not notice that it is not O1. But as soon as you're having bigger arrays, it is not O1 anymore, because V8 has this optimization that it just, when you shift for small arrays, it will say, okay, the array does not start at 0 anymore, but now at 1, now at 2. So they just skip internally these parts, but keep the elements still there. And quadratic is already really expensive. We don't want that. It's easy to see that this is expensive here, and that it's slow, but when you have like a deeper nested thing, maybe from one module, and then you have another module, and you just call a function in a loop in one module, and you don't see it immediately, right? It's more difficult to analyze this part. So sometimes it's good to inline some code. That way you will see what your actual complexity looks like. I would like to show you very, very, very brief. Don't have a lot of time. Some coding examples. I'm not really sure if this is. Let's get here. So here we have some code. It's functional programming. I want to just show you some. Okay, nope. We just have to make it like this. All right, so I just already executed a couple of things, and I'm going to just show you the examples because we are so little on time. So the top one, is the modular one, which is internally in V8 an optimization. So the fast one is actually using a higher modular one because the CPU is able to optimize something internally when the number that you're using is n to the power, 2 to the power of n. And that is able, the CPU is able to very fast calculate these things internally. And therefore, even though the other number is lower than the next one, 1,000, I don't know which one I use, 2 to the power of 5, yeah, 32, is only taking 120 milliseconds, yeah? And the 31 is taking more than 200 milliseconds. So that's quite a difference. Below, I benchmarked the functional programming style. So we have 3 operations behind each other. Map, filter, reduce. Very simple mathematical things doing there, just some weird stuff. And I just did the same with a regular for loop. And there is a huge, huge difference. So this is about 15 times faster to do with a regular for loop. And I do the same thing. The results are identical. So functional programming can be really slow. Shift, I already explained it pretty much. Let's not go into this. This is like small arrays. There's a big one. So here it becomes very expensive because this is seconds, this is milliseconds. Then what did we optimize in Node Core, for example? Well, sparse array inspection was very expensive at some point. Like in 8.3, it took 1.8 seconds to print this part, but it had not really anything to do. So I optimized the algorithm to 01, and now it only takes 76 milliseconds. That's quite an improvement, I would say. Quite a nice one. Then dense array inspection also got optimized. In this case, also the allocation is mainly the point. Because internally, I'm using a V8 function where I don't have to use object keys anymore. With object keys, I have to get all the regular indices for an array, and then I have to analyze it. But now I'm able to skip that part. So I don't have to allocate this information anymore, which was useless for the inspection in this algorithm. What else do I have here? Yeah, I'm already running over time, so let's go back to the slides. We have the Node ecosystem, which might look like this because you have like a huge bunch of modules out there, right? And like only a very small part of it is actually your code. And when we look at that, it's also really difficult to decide on what module to take. Sometimes it's about bugs, you know, like in Node ecosystems, you sometimes have like 10 modules that all do the same thing, but one has one bug, another one has another bug. But performance is also one reason. And when we compare it, so people came up with faster things, you know, they wrote a module, then they wrote something, named it faster. Someone else came around, also fast, you know, faster. I wrote the last one. And I didn't name it fast, so please, if you're optimizing some code, someone else who's smart might come in and just optimize it later on and find a better way to write it. Don't name things fast, because fast is a very relative term at that point of time when you only compare it with a few things, right? So yeah, try to dig really deep when you are looking at optimizing your code. You have to understand how your code is actually executed underneath, maybe even sometimes down to the CPU level. But that's very rare. This is mainly when you have to, like some really complex stuff maybe. But it's always good to understand how these things work, because then you will immediately understand, okay, this part might be more expensive than another one. You know where to look for, pretty much. If you refactor your code and simplify it, and this will always improve the code quality, and therefore also normally the runtime of your application. And you will save money because we know about these cloud providers that we are using, and we don't want to lose any users. Mainly focus on fast pairs. Don't optimize everything in your application. This would be a waste of time. We can optimize code in a wonderful way, and no one can read it maybe afterwards. Hopefully they do. But if we just focus on the real pain points, that's the important part. Please do that. Use streams. This is like using chunks, when you're handling data. Don't read everything in memory first and then handling it. And think about memory when you're having like functional programming and stuff like that. Memory is relatively cheap, but it can be expensive at times, especially when you have a memory leak. Yeah, and if you want to try this, contribute to open source. Yeah, thank you very much. Or Jikin. I tried it so often.